Hi, everyone. Thank you for having me. Yeah, I'm Andrew, and I'm going to be telling you, as Steve said, about low-frequency gravitational waves, which have only recently been detected. And so we're really looking at the universe in a new way for the first time with these. To get started, this all really goes back to Einstein and his theory of general relativity. To remind you all, Einstein's theory of general relativity tells us that what we perceive as gravity and the motion of an object around a massive body, such as a planet or a star, is really caused by distortions in space-time near these massive objects. Like in the figure that I'm showing here, the Earth's gravitational field is basically being shown by this kind of mesh that we see in 3D around the planet. And as we get in closer to the Earth, space-time gets more and more distorted. And this is what we see as gravity. Everything that's moving around and orbiting the Earth is really just kind of following along within this distorted space-time. Now, one of the predictions of general relativity are objects called black holes. These are areas of space where the curvature of space-time, gravity, is so strong that nothing can escape, not even light. Anything that goes in, that's where it's going to be until basically the end of the universe, or at the very least, till many, many, many years in the future. Yeah, these have been predicted by Einstein's theory of general relativity, and we have a few different lines of evidence for them. One of those lines of evidence comes from some of the gravitational waves that you've maybe heard about before from LIGO. We've seen we've seen black hole binaries, not supermassive black hole binaries in this instance, via their gravitational wave signatures. So gravitational waves themselves are basically these ripples in the fabric of space-time. If there's any Doctor Who fans, you might know wibbly wobbly, timey-wimey stuff. It's a pretty apt description, actually, for gravitational waves. It's the fabric of our universe, basically just rippling out. These are caused by very massive objects that are accelerating. In particular, usually we're looking at things called called binaries. For LIGO, they look at what are called compact binaries. So here I have a little video, if it'll play. Yeah, so here we have a video of two neutron stars, in this case, orbiting each other. They're accelerating as they orbit. And you can see that they're emitting all of these gravitational waves, these ripples kind of coming out from them. And as they orbit, they get closer and closer, and more gravitational waves come off faster and faster until eventually they merge together. Just a second here. Yeah, they merge together. We get more and more gravitational waves, but then the gravitational waves calm down since the resulting merged remnant is no longer accelerating. It's just sitting in place and there's no more gravitational waves coming from it. So, as Steve mentioned, the first time that we detected gravitational waves directly was about 9 years ago now, in 2015. LIGO in Hanford and Livingston, Louisiana, detected gravitational waves passing through the Earth, and these were determined to come from a merging black hole binary. This is not a supermassive black hole binary. This was a more stellar mass type binary, so the masses of the black holes were comparable to the mass of our own sun. But this was amazing. We predicted gravitational waves for nearly a century before actually observing them. Again, gravitational waves are predicted by Einstein's theory of general relativity, and that came out in the early 1900s. So, in fact, I believe it was 1916. So it took 99 years for us to actually see gravitational waves for the first time. Of course, this is just one frequency band of gravitational waves, though. So you're probably all familiar with light and electromagnetic radiation, and the fact that electromagnetic radiation comes in a spectrum. We have low frequency electromagnetic waves down in the radio, up through microwaves, infrared, visible light that we see every day around us, of course, and then going up into higher frequencies such as ultraviolet, X-rays, and even gamma waves. Well, it turns out that just like light, gravitational waves also exist on a frequency spectrum. So what I'm showing here now on the right is a plot showing our three main detectors that we usually think about when we think about gravitational waves. So we just talked a little bit about LIGO up here at high frequencies. It's LIGO sensitive to frequencies around 5 hertz to around 20,000 hertz, so 20 kilohertz. And as we said, it's sensitive to gravitational waves from stellar mass compact binaries. So these are either black hole binaries or neutron star binaries, or even a black hole neutron star binary system. Going further down in frequency to the millihertz regime, we have LISA. This is going to launch in 2037. This is going to be a gravitational wave detector that is in space. It operates very similarly to LIGO, but is going to be on, well, a much, much larger scale. I think if I remember right, the arms of LISA, the interferometry arms, are going to be on the order of a few 100,000 kilometers. So it's going to be on a very, very large scale. And then finally, down here in the very low frequency regime, we have pulsar timing arrays, and these are the gravitational waves that I study. So these are nanohertz gravitational waves, or for those of you who like to think in periods, these are periods of around 30 years for these gravitational waves. And these come from supermassive black hole binaries. So the largest supermassive black holes in the universe, these are hundreds of millions of times the mass of the sun. And we are now detecting these for the very first time. So before we get further into the gravitational waves though, just want to give you a little bit about supermassive black holes and supermassive black hole binaries. So supermassive black holes are, well, they're a lot like what they sound like. They are black holes, but much, much, much bigger. They can have masses millions to billions of times the mass of our sun. And we think that they actually reside at the centers of most massive galaxies in the universe, including our own. The Milky Way has a supermassive black hole at its center called Sagittarius A star. If you follow black hole news at all, you may have heard a few years ago that we took a picture of our own galaxy's supermassive black hole for the first time, which was very, very exciting news. But I'm not here to talk about Sagittarius A star. Instead, I'm here to talk about supermassive black hole binaries. So similar to how a supermassive black hole is basically what it sounds like, a black hole that's very, very massive. A supermassive black hole binary, also what it sounds like. It's a supermassive black hole, but two of them nearby each other and co-orbiting each other in this binary system. The way we form a supermassive black hole binary is through galaxy mergers. When we look out into the night sky, we know that galaxies merge because we can see them merging. We have plenty of pictures of two galaxies that are very close to each other and interacting gravitationally and are headed towards each other, falling in together. Of course, when two galaxies merge, if they both have a supermassive black hole, well, they're going to form a binary. It's not like one of those black holes says, all right, peace, this is your galaxy. I'm going to go chill over here in some other part of the universe. No, instead, both black holes are going to fall towards the center of the remnant galaxy, the galaxy that's left over after the two galaxies that were merging have actually merged together.
What determines which one's the remnant galaxy?
Well, neither of the progenitor galaxies are the remnant galaxy. It's really what galaxies formed after they both come together. So it's a mixture of both of the progenitors.
That's like milk dramina when that happens in however many billions of years.
Basically. But yeah, so the supermassive black holes fall towards the center of the galaxy remnant. And after about 100 million to even a billion years, it's a very long-lived process, the black holes will get close enough to bind gravitationally. Basically, they start acting under each other's gravitational pull instead of the pull of all the stars in the galaxy around them. And they form what's called a supermassive black hole binary. That supermassive black hole binary will orbit each other and slowly decay in that orbit until eventually they get to less than a light year separated from each other, at which point they'll start emitting significant amounts of gravitational waves. Now, I really want to emphasize just how small that separation is. The distance from Earth, or from our sun to the nearest star system, is about 3 light years. I think a little bit over that, even before. Either way, it's a longer distance than we're talking about here for these supermassive black hole binaries. So it's really only at these really, really tight separations that they start emitting gravitational waves. And we really can't actually resolve that. So the only way to really see these systems is by looking for these gravitational wave signatures.
Question?
Yes.
Why don't they merge?
Hmm?
Why don't they merge?
They do. It's just a very, very long-lived process. It takes millions of years for them to
So
actually,
they'll stay as a binary for who knows how.
millions of years.
Yeah.
Yeah. They do eventually merge, specifically as they orbit each other. Those gravitational waves will actually take energy out of the system. And as that energy is taken away, that's what causes them to come closer and closer together, similar to the video that we saw towards the beginning. But in this case, the supermassive black holes are just so much larger that it just takes a much, much longer time. All right. Yeah, so the way we detect these gravitational waves are with what are called pulsar timing arrays. So what we've done is we've basically said, let's try to figure out a way to detect these gravitational waves. They're really long. They have very, very long period. In fact, because their periods are so long, 30 years, well, that's 30 light years in period. You need a very, very long interferometer arm in order to detect those. Basically, a way to understand what did space-time look like at one point that's more than 30 light years away versus how does it look here. One way we can do that is by looking at pulsars. So pulsars are spinning neutron stars that are emitting beams of radiation. They're basically like galactic lighthouses. So you can see a few pulsars here in the background here, these little neutron stars with these beams of radiation coming out of them. And as the neutron stars spin around, the beam occasionally passes through the Earth. We get a very regular blip. In fact, it's a very, very regular blip. These pulsars are actually some of the best clocks in the universe. In fact, up until the 90s, pulsars were better clocks than atomic clocks. So it turns out the universe has given us extremely good clocks if we just look. And it turns out that if a gravitational wave passes between the Earth and the pulsar, since it changes space-time, distorts space-time, it changes the distance between Earth and the pulsar. And so that changes the timing of when we get those little blips. And if we know how the pulsar was supposed to blip at us, and then we observe a slightly different blip, we can start to figure out, oh, maybe there's a gravitational wave here. Now that's really hard to do with just one pulsar. There's a lot of different things that can go into that exact timing and the timing that we actually observe. So instead we look at entire arrays of pulsar. That's why it's called a pulsar timing array. We look at many, many pulsars at once, and we look for all of these little tiny timing deviations in all of these specifically millisecond pulsars. Basically pulsars that are blipping at us every few milliseconds. By then comparing all of these timing deviations across all of the different pulsars in our pulsar timing array, we can then reconstruct what the gravitational wave signal is across all of the pulsars. And that's how we actually detect our gravitational waves in pulsar timing arrays. Now, there are several pulsar timing arrays all around the world. So already, Steve mentioned NANOGrav, which is the pulsar timing array here in North America. It's a collaboration across the United States and Canada. But there are several other pulsar timing arrays around the world as well. There is the European pulsar timing array in Europe, the Chinese pulsar timing array in China, which uses the FAST telescope. There's the Parkes pulsar timing array, which is the Australian collaboration, the Indian pulsar timing array, and the Meerkat pulsar timing array, which are both new pulsar timing arrays that have just started taking data in the last few years. And most of these pulsar timing arrays actually collaborate together in what's called the International Pulsar Timing Array. So all the pulsar timing arrays take their own pulsar data and look at it individually, but we also know that we can actually do better by combining all of our data. Part of that is just because, well, in North America, we only really get the northern part of the sky. If we combine with, say, the Parkes pulsar timing Parkes pulsar timing array in Australia, which sees the southern sky, they see more pulsars, and so we can correlate between more pulsars and get a better idea of what our gravitational wave signal looks like. All right, so that is all of our pulsar timing arrays, though. So I want to bring this all kind of together now and basically show you a video that gives a nice summary of this entire process of merging galaxies to supermassive black hole binaries, to gravitational waves, to pulsar timing. So we can see that we have our two galaxies merging together, each one having a supermassive black hole at its center. And as we zoom in, we can see the supermassive black holes are orbiting each other. And you can kind of see, it's a little choppy here, but you can kind of see that as they orbit each other, there's gravitational waves coming out across this green mesh, being emitted by this supermassive black hole binary. Yeah. Those gravitational waves then are emitted out across the cosmos, across the universe, eventually traveling to the Milky Way, where then we can detect them using our pulsar timing array. So you can see we have the blips coming from the pulsar, and as the gravitational wave goes through, those blips either get here slower or faster, with their timing being changed by the gravitational wave as it passes between the pulsar and the Earth. And then in our pulsar timing array, we then look at many, many pulsars doing this same thing and figure out the correlated timing deviations between all of the different pulsars to understand what was the actual gravitational wave signal as it passed through us here at the Earth. Okay, so there's a few different types of signals we actually expect to see from these nanohertz gravitational waves. The first signal that we expect is what's called the gravitational wave background. This comes from the cosmic population of supermassive black hole binaries. And this is what we presented evidence for in June of 2023. For the first time, we had enough of a clear correlated signal between all of our pulsars to say, we think we're seeing the gravitational wave background. Now, we're not quite calling this a detection just yet. We're trying to improve our signal to noise ratio here a bit. But right now, we're pretty confident in saying that we have a gravitational wave background that we're seeing in the universe and that we're able to see in pulsar timing arrays. This is the Agassiz et al. 2023 is the paper for NANOGrav, but we're actually not the only ones to see the gravitational wave background at this point. So the European pulsar timing array, Indian pulsar timing array, Parkes pulsar timing array, and the Chinese pulsar timing array also all simultaneously announced evidence in their own pulsar timing array data for a gravitational wave background as well. So the fact that we're not the only ones seeing this either also gives us a bit of confidence. And we are currently in the process of actually combining all of our data as part of the International Pulsar Timing Array to see if we do get a better signal to noise ratio here. It's a very complicated process, but stay tuned. I think in the next couple of years, we're going to start seeing, it'll be the third release of the IPTA. Right, that's our gravitational wave background. That's just one of the signals we expect to see. This comes from our cosmic population of supermassive black hole binaries that I'm showing here, where we're basically getting gravitational waves from all of these supermassive black hole binaries at once. And it kind of just comes at us combined, and we're not really seeing individual supermassive black hole binaries. We're just kind of hearing the entire population. The other type of signal we expect to see are what are called continuous waves. These are gravitational waves from individual supermassive black hole binaries. These are called continuous because it takes millions of years for the black hole binaries to actually merge. And so if we see gravitational waves from an individual supermassive black hole binary, we're going to be seeing those gravitational waves for millions of years, or as far as we're concerned with our own human timescales, it's going to be an eternal gravitational wave emitter, which is why we call it continuous. It's basically going to be there forever. Astronomers really like to name things in a very straightforward, it is what it is type of way.
Can I ask another
Oh, yeah.
question? I'm sorry to hog it, but does the gravitational wave, does it behave as a wave or a particle?
It behaves as a wave.
So it's not like what light has.
Not as far,
both.
not as far as we can tell, but we're also still really at the beginning of gravitational wave science. I don't know as much about it, but I do know that particle physicists have ideas about gravitons and ways we might be able to treat gravitational waves similarly to electromagnetic waves. But we're really at the beginning of this science here. After all, we only detected the first gravitational waves 9 years ago, and it's only now that we're even seeing into another frequency band. So I think it's a very exciting time because we're just really starting to look at the universe with an entirely new messenger, basically. But yeah, so right now we haven't detected any continuous waves, but that's kind of what we expect. We expect our continuous wave detection will lag our gravitational wave background detection by about 5 to 10 years. And this basically comes down to differences in how the signal to noise ratio of our gravitational wave signals scale when we're looking for a gravitational wave background versus when we're looking for a continuous wave. So we really, for a gravitational wave background, we get the best signal to noise ratio by just adding pulsars to the array. But for a continuous wave, we actually benefit a lot more from just timing those pulsars for longer, as well as improving our ability to time those pulsars. So right now we're kind of in the exact spot that we expect to be as far as what we have and haven't seen. All right, so that's the two types of signals that we can see, but that can be a little bit abstract. So I actually like to analogize this to something a little bit closer to here on Earth, which is if you ever go to some sort of a crowded venue or a festival or something like that. Now, if you've been to a festival or crowded restaurant, crowded bar, whatever your favorite crowded situation is where you're maybe there with some friends, you'll know that with all the people there, there's usually a lot of noise. You hear kind of a background hum from the crowd. Everyone's talking, having a good time, and making noise. But if you're listening there, you're probably going to have a lot of difficulty picking out individual conversations. This is like our gravitational wave background. Our background is really just this hum that's kind of in the background where you can hear the overall noise, but you're not really going to be able to pick out any of those individual conversations that are going on. Now, if you're at a crowded venue or festival with a friend, you'll of course know that, well, no, it's not impossible to hear anyone. They just have to be loud and nearby to you, so that way you can actually pick out what they're saying. And this is like our continuous wave sources. Basically, when we do eventually see continuous waves, we expect that they're going to come from the most massive supermassive black hole binaries and the nearest by supermassive black hole binaries. Basically, they have to be in a place relative to us that they're going to be loud enough to come out across the background and rise above it. But ultimately, this really is what our signals are like. It's really a lot like just having a crowd that you're trying to listen into, and you're really only going to be able to hear a few individual people. Okay. Now, we have heard our gravitational wave background for the first time, and we're starting to analyze it. So I'm sure that you all probably want to know, have we learned anything yet? Are we taking all this time listening for the background and going, we heard that time? No, we're of course going to analyze what we actually hear and try to understand our universe better based on the gravitational wave signals that we're seeing. And the first thing that we actually noticed is that our gravitational wave background is really, really loud compared to what we expected. So before we'd actually detected the gravitational wave background, we had some ideas for what it might be and for how loud it might be. This is because, again, we can look into the sky and see galaxies merging. Since we can see galaxies merging, we can infer how many supermassive black hole binaries there might already be. And based off of that data, we expected a gravitational wave background that was a bit quieter than the one we actually heard. In fact, if we try to adjust our models to match the gravitational wave background that we're actually hearing, what we find is that we actually need 5 to 10 times as many supermassive black hole binaries as we thought we had in the universe before. This is really, really surprising. This is something that we're still in the process of trying to understand just what's going on here. In fact, it's so surprising and it's such a loud background that needs so many more supermassive black hole binaries that we're actually having difficulty reconciling this with what we already know about supermassive black holes in general. So not just supermassive black hole binaries, but even if we just look in our local universe at nearby galaxies, we can understand what those supermassive black holes are and how big they are. And the gravitational wave background we're seeing seems to suggest that no, we should have more really, really big supermassive black holes that we don't actually see nearby. So something's going on here. And this is all basically cutting edge research right now. We don't have an answer for why our background is so loud compared to our supermassive black hole population. And this is something that we are, I think, going to have to take a few years to really struggle with to really wrap our heads around and understand. But it's really fascinating. Clearly, we don't understand everything about our universe. And this screaming loud gravitational wave background is telling us that. Now, in addition to how loud the background is, we can also break it down as a spectrum, which is what I'm showing on the right here. And so basically the way to read this plot is the horizontal axis is our gravitational wave frequency, and the vertical axis is how much of a timing residual we expect those gravitational waves to induce in our pulsar timing arrays as a function of frequency. And so the blue violins are the strength of the gravitational wave background at these different frequencies that we actually measure, with the strength being most confident at the areas that are widest. And then we think, maybe it's less likely that it's going to be as loud as here, where it's a lot narrower, or as quiet as it is down here, where it's also narrower. And then what I'm showing in black and in red are two models of this gravitational wave background that are based on supermassive black hole binary populations. The one in black is a more naive model that makes some simplifying assumptions, whereas the model in red shows a gravitational wave background model when we account for all of our supermassive black hole binaries in the universe, with the spread then just being, we did this 1,000 times to understand different gravitational wave backgrounds and what we should expect compared to what we're actually seeing. And one of the very exciting things that we're seeing is here at 16 nanohertz, we have what appears to be a little bit of an excursion. There's a little bit of a bump in our gravitational wave background. And so far, we haven't been able to confirm exactly what it is yet. But what we have been able to confirm is that it's consistent with a supermassive black hole binary that wouldn't have been detected in our continuous wave searches yet. So there's a lot more work to do investigating this, because this could also just be noise from our pulsar population and some mismodeling there. But it could be that the gravitational wave background signal that we're measuring right now is starting to hint at these individual supermassive black hole binaries and might be starting to tell us where to look for them. And that's a really good thing because turns out it's easier to find supermassive black hole binaries if we know where to look. I mentioned earlier that we're probably about 5 to 10 years out from detecting continuous waves. We're a little impatient as astronomers. We don't really want to wait 5 to 10 years. So we've been looking around to see if there's a better way to try to detect these and to improve our sensitivity. And it turns out that we can actually improve our sensitivity using what are called targeted continuous wave searches. Right now, when we search for continuous waves, we search all of our data, all frequencies over the entire sky. It's very computationally expensive, and we don't do as well as we think that we can. Targeted continuous wave searches allow us to do better by knowing where to look. So before I go more into that, I'll tell you a little bit about quasars, which are supermassive black holes that are accreting matter. The reason we care about them is because they're going to help us know where to look for the supermassive black hole binaries. So when you have matter around a supermassive black hole that's falling into it, all of that gas will heat up as it gets closer to the black hole. You basically have a whole lot of dust and gas that's getting squeezed into a smaller and smaller space. And as it squeezes together, all those particles bump against each other and heat up. It gets very, very hot and very, very bright. In fact, quasars can outshine entire galaxies. That's how bright they get. And it turns out that simulations tell us that if matter accretes onto a supermassive black hole, the light will periodically brighten and dim, like in the plots that I'm showing here. These are showing basically as a function of time on the horizontal axis, how bright each of these quasars are on the vertical axis. And we can see that it looks fairly periodic. Seems like there's a sinusoidal variation, happens regularly. And it turns out that our simulations say that this could be associated with a supermassive black hole binary. And if it is associated with a supermassive black hole binary, then we should look there, because it turns out that if we know exactly where to look in the sky as well as in frequency, our continuous wave searches can actually do about 10 times better in their sensitivity. So instead of having to wait for 5 to 10 years, we might actually be able to start seeing some of these in the next year to 3 years if we know where to look and if we're lucky. So the caveat with all of this is that regular quasar activity can also look very sinusoidal. So a lot of these could actually be false positives. In fact, most of them probably are red herrings and are not actually supermassive black hole binaries. That being said, it's still a starting point. And that's really the point we want to emphasize with all of these, is that even if not all of them are real, it still gives us a place to start looking for these continuous waves that is better than just trying to look everywhere at once. If we go back to our analogy about the crowded room or a restaurant, the way these targeted searches help us is a lot like if you can actually look at someone when you're trying to listen to them in one of these crowded situations. You do a bit better by trying to basically read someone's lips than trying to just listen.
One of the targeted sources, would that be elliptical galaxies by any chance?
Some of them, yeah. So elliptical galaxies, we think, have gone through a merger with some other massive galaxy, which is why we think they're elliptical. And so that is actually one of the places that we are also looking. We take a few different strategies with trying to look for these supermassive black hole binaries and doing these.
And a follow-up question. I equate the interferometer size to wavelength with radio signals. Lower you go, the lower you go in frequency, the higher you go in wavelength. So obviously, if these were radio waves, you'd be talking about antennas that were huge. So the interferometers are basically the same thing. So my question is, how do you use the interferometer setup to actually determine direction as to where these things might be located?
So that basically comes down to, so our interferometer is the pulsar timing array. And so that basically comes down to kind of how strongly we see the signal in a given direction of the sky. Really, how much is that gravitational wave changing the timing deviation of our pulsars? And we can basically correlate that with a direction.
Yeah. So you're taking all of those calculations together and it's kind of giving you a place that the antenna's pointing, so to speak, to simplify it.
Exactly. When we look at our pulsar timing arrays, we're looking at the entire sky at once, effectively.
Mhm.
And so in that sense, we don't have a particular direction, but we do know that gravitational waves are coming from particular directions. And so, yeah, they come a bit strongly in the direction that they're actually coming from. So we should see that in the pulsar data. Yeah, so that actually brings me now to the end of my talk. So to summarize, we have now found evidence for a low frequency gravitational wave background for the first time. And that gravitational wave background is telling us information about supermassive black holes, supermassive black hole binaries, and galaxy mergers. And some of that information is really, really surprising, especially just based on how loud this gravitational wave background is and what that would mean for our supermassive black hole population. It would need more, and they would need to be much more massive than the ones that we see nearby. Finally, we have a few things to look forward to in the future, particularly with continuous wave searches and with targeted searches for continuous waves. Thank you.
Any other question?
Yeah, I do have another one.
You already have two.
Okay, go ahead.
My question's actually kind of similar to Matt's in terms of like the directionality of the signal and how it's calculated from the pulsars. In doing that, are we able to have any of these projects started kind of creating a generalized map of the strength of these signals in various directions, kind of like we have with the microwave background, or?
Yeah, so that's another thing that we are actually looking at it's called anisotropy in the gravitational wave background. Basically, when we look at the sky, how bumpy is the gravitational wave background, and is it stronger in some places than in others? Like you said, it's very similar to the cosmic microwave background. Right now, we're just not sensitive enough to detect anisotropy. We look for it. We haven't seen anything yet, but our upper limits that we're placing are also really high. So we're kind of in the realm of, well, we're developing all the techniques, and as our data gets better, then we can expect to start to put constraints on anisotropy.
My other question was about distributed computing. Are you guys making use of that in this project? I know LIGO's, the LIGO satellite, there was tons of data that came out. I was actually involved in one of those projects. I had a number cruncher down in the basement, and I ran that for about 4 years for Einstein at home, and that was gravitational wave search. So I was just wondering if this project's going to make use of distributed computing.
When you say distributed, you mean like computing clusters?
Yes,
Yeah.
kind of like the BOINC projects, where they
Setting.
Yeah, or SETI. Yeah, SETI at home did the same thing. Einstein at home is doing.
Oh, where it's distributed across people across the internet.
Yes, yes.
So I don't think that there's any plans for that right now. We do use a lot of heavy computing infrastructure, but right now, most of the computing infrastructure NANOGrav uses we have a specific grant for a computing cluster for NANOGrav. So that runs a lot of our data analysis. And then since we're a collaboration among several universities, researchers also then use their own home university computing resources as well. I very regularly use the computing clusters at both Yale and at University of Connecticut.
Becomes a what do they call it, a proprietary kind of
Yeah.
thing too, where you guys want to be the first ones to discover something.
It's a little less about that. It's more, we do want to keep control over our software as well that we're using for all of these calculations, because they're very involved calculations. We're basically solving for a gravitational wave signal across 60
They wouldn't be able
galaxies.
to be used on a PC.
Yeah, I think that's one of the main challenges is how we would approach that in the first
Need a
place.
quantum computer.
Rick
And
and Bob?
can we assume that galaxy merges interactions, that supermassive black holes are the product of that? Or can a galaxy exist? We always read about most galaxies have a black hole at the center. Can they have two black holes? Can they have without a merger?
So probably not without a merger. And so
And if you have a merger, you got two supermassive black holes, but one could be considerably bigger than the other. Does
Yeah.
one dominate the other?
So that's a really good question. So most of the gravitational waves that we're sensitive to at pulsar timing arrays are from supermassive black holes that are very close in mass. In fact, we usually mostly consider supermassive black holes where the ratio of the larger to the smaller is at most 4:1. That being said, we can absolutely have more kind of lopsided black hole binaries. These are what we call extreme mass ratio in spirals. NANOGrav and pulsar timing arrays are not sensitive to those, but LISA will be sensitive to those when it launches. It's one reason we're really excited about that project.
Bob?
What's the wave speed of gravitational waves? Is it vary according to their wavelength or is it?
No, as far as we can tell, it's consistent with the speed of light. So we already thought that it would be just based off of general relativity, but we got very lucky, and I want to say it was 2017. LIGO saw a gravitational wave event coincident with a gamma ray burst near the center of a galaxy, and was able to actually localize it well enough to say that that was probably both events were probably caused by the same merger, and we got both of those signals at more or less the same time. Once we correct for things like all the dust and gas, the interstellar medium between us and that galaxy, the delay between the electromagnetic signal and the gravitational wave signal was exactly what we expected. So gravitational waves propagate at the speed of light.
Jim, you had one?
Yeah, with dark matter concentrations distort or deflect low frequency gravitational waves.
So that's a really good question, and that's actually currently under investigation. So we think that for the most part, it's not going to have a huge impact. So most of our modeling we've been able to approach without worrying about dark matter, and especially at the kind of higher frequencies of our low frequency regime, we don't think dark matter is going to really have an impact. But it might have an impact in the spectrum of the gravitational waves. So in this spectrum that I'm showing, it might have more of an impact down here at these lower frequencies. And basically at these lower frequencies, we expect that other processes can also affect the separation of the supermassive black holes in the binary. But as we get to these higher frequencies, the gravitational wave emission is what really drives everything. And so once we're up here, this should all just be influenced by the gravitational waves and nothing else.
One more quickie.
Yeah.
Do magnetars have gravitational waves?
They wouldn't, well, I think that depends a little bit on who you ask, and it's a little bit of an open question too.
Would you be able, could you differentiate a magnetar from no, I can't because it's too wide a thing. You're not that localized yet.
Yeah, and we wouldn't be sensitive to the gravitational waves from magnetars or any other kind of neutron star. But that being said, I want to say that it's going to be next. I think it might actually be LISA. One of the other gravitational wave detectors is expected to be sensitive to gravitational waves that might come from magnetars and other spinning neutron stars. And that is a big caveat there, because it all just depends on how the matter is distributed within the magnetar. And so the more symmetrical it is, then the fewer gravitational waves it would be able to emit. So basically, we don't get gravitational waves from really symmetric systems. You need some asymmetry in there. And so that's what the binary really does, is you have these 2 points, effectively point sources.
Are there any questions on that? No.
This technique of doing this with the pulsars, is this something that was kind of thought up as a result of what LIGO was doing, or is this something that we knew we could do, but we're waiting for like the right clocks and the right amount of computing power?
So more the second one, but not for the reasons you listed. So this is something that we've known that we've been able to do since I want to say 1987 was the paper that showed that you could actually do this. The Helens and Downs paper, basically they did the calculations showing that gravitational waves would induce these types of timing deviations in a pulsar. So we've known about this for a very, very long time. What we had to actually wait on was enough data. So yeah, these are 30-year periods. And so you really can't even begin to dig into that until you have, well, in this case, 15 years of data was actually enough to start to see this, but we needed actually 15, really, it was 16 years of data in the actual data release before we were able to detect these gravitational waves. On the flip side, the more data we take, the more sensitive our detector actually becomes. So as we keep taking data, we automatically become more sensitive to gravitational waves.
Gravitational waves are created by these massive object interactions. About 1960, there was an English physicist, Peter Higgs, who theorized the Higgs boson, force carrier. And they actually, I think, discovered that it actually existed about a dozen years ago from the Super Hadron Collider.
Yep.
How does the Higgs boson figure into the creation of, or imparting the mass to matter or particles? And how does that translate into gravitational waves?
So there's really not actually much of an overlap there. So my understanding, the Higgs particle and the Higgs mechanism is really, it's what gives matter mass. And so in that sense, you know, it's what gives our supermassive black holes mass. But beyond that, we actually don't really have to think about Higgs interactions at all when it comes to our gravitational wave systems. It really just comes down to general relativity.
Yeah, like where does the Higgs boson, how is it enabled or created to impart mass to objects?
That I don't know very much about. Yeah, you'd need to consult an expert on the Higgs particle.
But the gravitational waves are simply a product of the interaction of massive objects.
Yeah, it's specifically due to their motion through space-time, and as they accelerate, they create ripples in space-time. But the Higgs mechanism just doesn't come into that.
Any other last questions? Thank you.